So another converter I would like to discuss is the SEPIC converter. So SEPIC is similar to Çuk converter, as we will see, but it has some differences. So SEPIC is short for single-ended primary inductor converter. So actually Çuk converter was a double-ended inductor converter, but this one has a single-ended primary inductor. So actually if you compare it with the Çuk converter, that side is same. The only difference is the diode and the inductor position has changed. Again, we will derive it mathematically, but I would like to discuss it first. This is also a buck boost converter, so you can generate both lower and higher voltages than the input, and also that converter actually produces a positive voltage. Okay, so the polarity of the output voltage in the Çuk converter was reversed, so it was producing a negative voltage, but SEPIC converter actually produces a positive output voltage. Okay, so it's essentially a boost converter. Actually, if you have a look at that side, okay, if you recall the topologies of the first semester, so that part is like a boost converter. Okay, so and actually if you look at that side, okay, so that side again is the simple case for a buck converter, which you supply the current, and when you charge it, actually you are supplying through the load, so it is just reverse. So it is a kind of boost added in series with a buck converter. Okay, so then they are commonly used in battery powered systems because the voltage level can be adjusted quite easily, and you are again getting a non-inverting output voltage, and that can be controlled. And again, it is quite popular in automotive industry or that kind of applications. And again, there's some possibility, we will talk it later on, but there's a possibility to turn off the converter completely. Okay, if you close that switch, for example, if you close that switch completely, then that LC and L circuit connected the constant voltage, once that capacitor is charged up to the input voltage, there will be no current drawn. So it is completely safe to turn off this converter. Okay, so let's look at the operating modes, and actually I'm going to upload a couple of handouts to the OTTI class, so please have a look at those files, and I will put the same documents into the video description. Okay, so now let's have a look at how it works. And actually, if you had an understanding of the Çuk converter, it is more or less the similar logic. So again, we have two inductors, we have a single capacitor in between these two. So actually, once this is the default inductor current direction, and this is the default current direction for the second inductor. So when I close that switch, okay, when I close that switch, I know that inductor is being charged, like as if it is a boost converter. So the current in the first inductor is keeping up. Okay, and actually if you take the current direction in that way, and once we have a voltage polarity, again we will prove it. So it is, you are connecting a positive voltage source like a capacitor connected into a inductor. So again that will increase the current. So again it is the same logic. So first we are charging the inductor using the input voltage, and we are charging the second inductor using the capacitor. And once we open that switch, okay, let me use a different color. Once we open that switch, actually now that inductor current will charge the capacitor, and they will combine, and they will actually supply the load with the help of the current in the second inductor. So again, first we are using the switch to charge the both inductors, then we are opening the switch, and those charged inductor currents, the first one supplies the capacitor and the second one supplies the output capacitor and also the load. Okay, so let's look at the operating modes again in detail. So at first, again, this is the on state, and once we have it here, so again we have a second loop through here, and I can say the inductor voltage VL1 is equal to Vs. And again here I can say like VL2 is equal to VC1, right? So what can I say about the VC1? So in order to calculate the capacitor voltage, let's go back and have a look at the previous slide. So let me clean that part a little bit. So again, if you have the switch closed, or if you have that switch open, okay, so what I have is that loop. Okay, that loop is always there. So actually I can write, on average or instantaneous, I can write the Kirchhoff voltage law, and I can get the relation between all those voltages, right? Okay, so let's start with that one. I can write put it like that. So I can write like minus Vs through here, okay, plus VL1 plus VC1, and there's opposite direction minus VL2, that will be equal to 0. And this is for instantaneous and average voltages. Again, I know in the steady state, okay, in the steady state, so VL1 should be equal to 0, and VL2 on average average voltages, right? So these two should be equal. Again, there can be some change with respect to ripples, because whenever there's some ripple on that one, there will be some voltage. But in this case, I make the assumption, okay, so because if you really would like to solve the instantaneous voltages and currents, you need to do a second or even higher order equations. So I assume C1 is large enough, and we will verify that one. So VC1 is constant. Okay, so if I use these two property, I can eliminate that one and that one. Since they are equal to 0, I can say VC1 on average is equal to Vs. Okay, that capacitor voltage will be equal to your input voltage, Vd or Vs in this case. Okay, so I will use that information to analyze the inductor current, because here I know it is equal to Vc1 and that is equal to Vs, right? This is for on. Okay, so let's have a look at what happens when the switch is off. So now our switch was here, right? So now it is off, and now my inductor current flows in that direction, and my second inductor flows in the other direction, and I had the diode here. Now it is on and it is conducting. So now I can write, okay, I can write the same equation. I mean, we just wrote the Kirchhoff voltage law through here. Now I am writing it through that loop. Okay, so minus Vs plus VL1 plus VC1 and plus output voltage V output. Okay, so now I can write, okay, VL1. I cannot write like VL1 is equal to 0, because this is not valid for all. I mean, that topology is not valid for all switching states. This is just for the off state, and I will use the instantaneous value. But what I can say, if capacitor is large enough and its value is equal to Vs, actually they will cancel each other because Vc1 is equal to Vs, and I can write VL1 is equal to minus Vo during the off state. So this is the off state. So I can use these two property. I know the inductor voltage in the on state, I know the inductor voltage in the off state, right? So I can let me write it here. I think I don't have it. So I can use voltage seconds balance. So again, in the steady state, I know, like, on average the area under the inductor voltage will be equal to 0. So at first it was Vs for how long? For on state, so it is Vs time d time Ts, right, plus that voltage, which is equal to minus Vo, okay, times 1 minus d Ts will be equal to 0. Actually, I think that was, sorry, it was cropped. Let me write it here again. So minus Vo 1 minus d Ts is equal to 0, right? So you can get rid of that one, and you can actually write Vo is equal Vs times d divided by 1 minus d. So it is again a, buck, it's the same as a buck boost converter. But in this case, again, our output voltage is positive. Okay, so this is the biggest difference from the tube converter. So again, if you look at here, I think they are all combined and that one is missing. Sorry, I think this is the input, I think, of the inductor. So let's have a look at that one. So here, this is the voltage of our switch. So whenever it is on, it is 0, and whenever it is off, it is blocking our voltages. So again, you can have a look at the voltages over here, right? So again, the blocking voltage is V out plus Vc1, and Vc1 is equal to V in, so it's V in plus V out. So there's one kind of disadvantage. The voltage rating of the MOSFET or any device should be chosen properly to withstand those things. And the switch current is having like trapezoidal shape like that. And again, they are working consequently with the diode. So whenever the switch is on, diode is off. So whenever the diode is conducting, the switch is off. And the capacitor current, okay, it's positive and negative. It has that kind of trapezoidal shape. And again, as we have the voltage second balance, you can calculate the current balance on the capacitor, so they will cancel each other. Okay, and for the input current, okay, so whenever you are turning on the switch, it is charging up like a boost converter, then it is discharging. So again, you are still drawing that kind of continuous current from the source. Okay, so I will put a handout to the OT class and to the link, so please have a look at those things. Another nice thing about the inductors, actually, once you plot those inductors currents, okay, so they can be like charging and discharging at the same instance. Okay, so they are charging up and discharging at the same time. So the idea is, instead of using two separate cores for the inductor, you can use a single core, and the same inductor can be wound together, so they are called like the mutually coupled inductors. So in the overall, it helps you to increase the efficiency, and also from the volume point of view, you can achieve a smaller size. So again, I will upload a couple of handouts about that topic on the practical applications, so please have a look at those things as well. Okay, so to summarize, so the advantages of the SEPIC converter, it is producing a non-inverting voltage, so it's a non-inverting buck boost converter. So that is, you know, in the Chuk converter, it has many advantages, but having a negative voltage, you know, cannot be possible for some applications. So SEPIC solves that one, and it's like more energy efficient, and it's like battery converters and that kind of thing. So if you want to disable it, you can just turn it off completely. That's fine. And compared to SEPIC Chuk converter, remember you had inductor at the output as well, but in this case what we have is I mean, here we have a diode, right? So that diode, actually, whenever it is off, so you have this continuous current. So that is one disadvantages compared to SEPIC. So you have pulsating output current. Remember, in the Chuk converter, we have both continuous current at the input and at the output. Okay. Again, compared to SEPIC, Chuk converter, SEPIC converter uses that capacitor in the middle as the main storage element. So that capacitor has to be has to have some large capacitance, and it should have some large ripple current rating as well. Okay. So again, the control, I mean, if you want to implement the control yourself, it can be quite tricky. But there are some, you know, integrated solutions with some controllers embedded to the switches or the integrated circuits. So with those things, that shouldn't be a big problem. Okay. So, and inductors again can be combined to a single core. It's called the coupled inductors. I mean, don't worry about that concept. So we will be investigating using like mutual inductors or transformers in the power electronic circuits in the following weeks. So by combining that one, we will see it can be possible to achieve a lower, you know, inductors, and you can reduce the size, and that can also help to minimize the oscillations due to parameter changing and that kind of things. But we will discuss it in the following weeks. So the last topic that I would like to talk this week is the interleaved converters, at least just to make an introduction to interleaving. So interleaving is like working some things in parallel. For example, again, you know, you can connect like many converters in parallel. So for example, sometimes we want to increase the current rating, and instead of using a larger converter, if you already have a product or if you are already some solutions, so you can connect like 2-3 converters in parallel, so they are supplying the same output voltage and they are sharing the current output. So that's possible, but again, if you like turn on and off those things at the same time, okay, that may not be the best possible configuration. Actually, if you think about it, your internal combustion engines like normal automobiles are kind of interleaved. So those, you know, many cars doesn't have a single piston that is going up and down, right? Usually they have like 4 pistons in a normal engine, or even more. So, you know, again, they don't fire those 4 pistons like together, right? So what they are doing is they are putting some phase difference between those firing sequences, so they are working in pairs. So one of them is generating power and the other one is off. So at the end of the day, you are trying to minimize the torque pulsations, because if you just fire it at the same time of all those 4 pistons, I think that will cause lots of vibrations. So we have the same concept in the power converters by interleaving. I mean, in this video, I just would like to show a simple example as a interleaved buck converter. So here, what you see is, again, you have let's say this is some current and it is producing some current, and you can supply twice of that current to the output, right? Again, the thing that I was talking, like if you just turn on both of those switches and turn off those things at the same time, the ripples will combine in those things, and it will actually add on that capacitor. So either, you know, the size of that capacitor should be increased, or you will have a larger ripple voltage. Other thing what can be done is if you just put some phase difference between those switches. So if one of that, remember the inductor current, okay, so whenever you are connecting, it was having like that kind of waveform. It is charging and discharging, charging and discharging. So that thing has the same waveform. But if you can just put some kind of offset between these two, actually that one can be like free, maybe not free, but really minimized ripple currents. Okay, so let me show you the graphics here. So let's say you put some offset. Again, if it is like working at exactly at 50% duty cycle, it is possible to cancel out the ripples maybe completely. But for example, if it is working at 60% duty cycle, then there has to be some overlap periods. So here we have such a case. So this is the inductor. I think the duty cycle is around 40%, whatever. So you have that kind of current, and again the second inductor current is shifted, so you know, you are not turning on and off those converters at the same time, but they have the same duty cycles. There is just a phase difference. So once you do that, and once you add those currents, okay, so instead of having that ripple, okay, and actually if you combine these two in parallel, there will be twice of that ripple. What you achieve is like, you achieve like even a smaller ripple current. Okay, so by this way you will have a nice output, and actually you can reduce the size of the capacitor. So that, you know, trick is called like interleaving converters, and we will discuss that thing. And you know, again, by interleaving it may be possible to, you know, combine these two inductors in a similar or single core, or that kind of tricks. Okay, so please, also I put many reading materials. Please have a look at those things, and your first project will be based on the SEPIC and CHUK converter as well. Okay, thank you.